All right, the next situation that you might see, if you start out with a poor leaving group, and you know a poor leaving group, if a leaving group doesn't leave, you cannot do a substitution reaction. In this case, if you want to do a substitution reaction, we have to convert an OH, a bad leaving group, to a better leaving group. All right, we can use any hydrohalic acid like all the group 7 or TSCl, toisyl chloride that works. All right. Now, if you use hydrochloric acid, all right, let's see what happens. When you do that, the first step is going to be a proton transfer. Now, why do we do this? Because we have to convert an OH to a better leaving group first. All right. So this guy looks like a hydronium ion, and you know hydronium ion is a strong acid, right? Will dissociate in solution. If it dissociates, so proton leaves, go back to the static material. But in any case, this group can leave too. This the whole group right here can leave too, right? When that happens, that you go forward, you get carbocation right here, and then nucleophilic attack by chloride floating around, which is your reagent, right? Floating around right now, chloride attack, and you should get this compound. All right. In this case, we don't get two products, the pair of enantiomer, because this carbon right here is a chiral, right? It's not a stereocenter. It doesn't have 4 different substituents. So these two are the same thing basically. All right. So again, I don't want you to memorize. There might be proton transfer at the beginning. There might be proton transfer at the end. There might be proton transfer in the middle of these two main steps. Well, try to play it by ears. All right. If you start with a poor leaving group, well, what you have to do, you have to make it a better leaving group, or you cannot do a substitution reaction. And at the end, if you end up with after nucleophilic attack, if you end up with a positively charged compound, and you know that usually a strong acid, it will dissociate, it will lose a proton, become neutral. And that's the reason why we have proton transfer at the end. Try to be familiar with all this step, and when you actually draw the reaction mechanism on the quiz, play it by ears. We all play it by ears. Okay, just think about what you have to do at each step. All right. Now this one, if you start with if you want to do SN1 in each of these compounds, which one require a proton transfer at the beginning of the mechanism? Go back right here. Why do we have to do a proton transfer at the beginning? Because an OS group is a poor leaving group. It doesn't want to leave, right? It doesn't leave. So you have to make it leave by convert it to a better leaving group. All right. Who's here? Has a poor leaving group? Iodide, poor leaving group? No, that's an excellent leaving group, one of the best, right? OH, yes. The B, you have to convert it a better leaving group by using HCl, Br or HI. Those works, okay? B, good leaving group already. So a C, don't have to do anything. Good leaving group. In D, yes, you have to do something with it. All right, add a HBr. Convert it a better leaving group, and they will leave to form a carbocation. Okay. All right. Another situation that you will see, they might have a rearrangement. Right, that could happen. Let's see what happened here. Start with a good leaving group already. All right. Nucleophile is neutral. When it does nucleophilic attack, you will probably get a positively charged compound. You probably have to do proton transfer at the end. Okay. All right. So this reaction produced 3 products. 2 here, right? A pair of enantiomers and this compound. Let's see what happened here. So one step at a time, step by step. This is an SN1 reaction. The first step is going to be a carbocation formation. So leaving group leaves, you get carbocation. All right. And then the nucleophile ethanol will attack. You should get 2 compounds here. All right, so from wedge line and dash line, so 2 compounds. And then this is a strong acid, look like hydronium ion, right? So strong acid dissociate 100% in water. So not in water, in solution. Take a base, only base in the solution right now. Grab the proton. All right, so you get 2 products there. All right, so a pair of enantiomer, which is this. Now, how do you get this guy? Well, looks like the nucleophile attack this tertiary carbon, see that? Not the secondary carbon right here, it attacks right here, right? So you this guy has to attack right there. But how do you how do we make this guy attack the carbon in the middle right here? Well, we have to make it positive, right? I'm not sure if you realize that. What type of carbocation is this? This is the secondary carbocation. Can you make it better, more stable? Hydride shift comes in, a rearrangement, all right? And you're going to get a tertiary carbocation, which is more stable. And that's when a nucleophile come to attack. Ta-da! Right? You get only one product here because this carbon is not a stereo center, not a chiral center. All right? And now, are we done yet? No, positively charged product, not done yet. Right? So this oxygen is a strong acid. This will lose its proton. Take a base in the solution, lose the proton, you get that, the last product there. Okay. So we have a hydride shift here. And now if you ask me, what if we do a hydride shift from the right side? Well, you cannot do it because if you do it, you get a worse, less stable carbocation, primary carbocation. All right. Going further down here, in the case that we don't have hydride shift to do, an alkyl shift will take place. All right, look at this right here. So this reaction also goes SN1 reaction, but we don't really get this product right here. See that? Methanol doesn't attack here. It attacks the quaternary carbon instead right here. All right. So there's a rearrangement in there. All right. First step of SN1 reaction, carbocation formation, or form a carbocation. All right. So if you have methanol attack right now, you're gonna get the first product here. See that? It will attack at this position, but we don't really get it less than 1%. So basically, we don't get that. We get methanol attack on this position. So we're gonna check a hydride shift real quick. So hydride shift on the left side, you get worse carbocation. So we don't do that. On the right side, there's no hydrogen there. So that you cannot do hydride shift here, but you can do an alkyl shift here, or we call methyl shift in this case. So methyl leave, all right? Methyl go hop to the other carbon to form a carbocation at this place, all right, this carbon here, and then methanol attack. All right, so you get that product there. This is not a stereo center. You get only one product here. All right, are we done yet? No, we're not done. This is a strong acid. See that? Oxygen with a positive charge look just like hydronium ion. So we'll dissociate. A solvent come grab a proton. You get the product there. That's a product. There we go. All right. Okay. All right. Now, what you should know, what takeaway from this slide? Rearrangement. Every time when you see a rearrangement, when do you see rearrangement? When you see an unstable carbocation, usually primary or secondary. All right. And when a rearrangement does happen, hydride shift is faster than an alkyl shift. All right. If there's no hydride shift, of course, you're going to go to an alkyl shift, but look for a hydride shift first. Okay. All right. We're going to close right here. So if you look at this picture, so I saw this on the internet, looks like it's just a lake, a tree, and they got a couples right here, right? Can you see a baby in this picture? There's one big giant baby in here, in this picture. Look for it, and I'll give you an answer on the next video. Okay, there's one baby in here.